said, if not for electron-electron repulsion and for Pauli's principle, which we'll be going into detail in just a little bit, okay, the exact ground states would have been easy to obtain for a helium atom. Okay, you would just say assign both electrons to the 1s orbital. Okay, so you say there's a 1s2. You've heard of this expression in your freshman chemistry. For helium atom, the ground state is 1s2. But what we're really saying is if the configuration is 1s2, what we're saying is we're going to assign each electron to a 1s orbital. Okay, so this is actually an approximation, because what we really mean when we're saying that is that okay, let's just ignore for now electron-electron repulsion and Pauli's principle. Then you say, okay, electron 1 is in the 1s orbital and it's spin up, and electron 2 is in this 1s orbital and it's also spin up. They're both spin up. So if not for electron-electron repulsion, Pauli principle, ground state could either be this one. You have electron 1 spin up and electron 2 also spin up in the 1s orbital. Or you can have electron 1 in the 1s orbital spin down and electron 2 also spin down in the 1s orbital. Okay, remember when your variables are separable, your wave functions can just be multiplied together, right? Just like we did when we went from one-dimensional box to the two-dimensional box. We were able to separate the x and y functions, and you can and the overall function is just a product of the two. Right? So what's another way we could write the ground state? One S1 alpha 1 times 1 S2 beta 2. Right? What we're saying here is electron 1 is spin up and electron 2 is spin down. What's another way we could write this? 1s1 beta 1. So electron 1 is spin down. 1s2 alpha 2. Electron 2 is spin up. Okay? We would have expected our ground state for helium to be fourfold degenerate. Okay? 4 ways you can have it. But in fact, because of the electron-electron repulsion term, fundamentally these functions are of the wrong form. Okay? So none of these functions are acceptable. Okay? But in the orbital approximation, okay, we can ignore electron-electron repulsion. Okay, you might say maybe some of these are acceptable, maybe not. Well, let's take a closer look at it. Okay? All right. An important thing about atoms that have more than one electron is that electrons are indistinguishable. That means your wave function should not be able to tell you which of these electrons is electron 1, which one's electron 2. All you know is you've got, in the case of helium, 2 electrons. Okay, so electrons are indistinguishable. So anytime you have a wave function that's describing indistinguishable particles, okay, that wave function, we say, mathematically must either be symmetric or anti-symmetric with respect to exchange of labels for any pair of these particles. In other words, it doesn't matter which electron I call electron 1 and which electron I call electron 2. It's just a name, right? The wave function should give you the same physical state. Should be describing something. Should be describing the same physical reality. All right. So in other words, mathematically, then, if I were to operate what's called a permuting operator, p hat 1, 2. I forgot. I can't do a hat on this one. So p hat operating on a function of electron 1 and electron 2, that will just switch the labels between electron 1 and electron 2. Okay? So if the function is symmetric, then if I were to apply p hat 1, 2 on function f, I should just get back the same original function. in that case, we say the function is symmetric with respect to the exchange of labels for particles 1 and 2. If I were to operate P12, the permuting operator, on function f, and I get back the negative of f, okay, then we say that that function f is antisymmetric with respect to particles 1 and 2. In other words, a function is symmetric or antisymmetric if it's an eigenfunction of the permuting operator. What would be the eigenvalue? +1 if it's symmetric. The eigenvalue is -1 is antisymmetric. Okay. Otherwise, if it's not an eigenfunction, you say it's asymmetric. Okay. So we have symmetric, antisymmetric, and asymmetric. In order for a wave function to be acceptable, if it's going to describe indistinguishable particles, like indistinguishable electrons in an atom, that function must be either symmetric or antisymmetric with respect to the exchange of the labels for these indistinguishable particles. Let's just clarify exactly what we mean by this permuting operator. Let's say you have a function of x1 and x2, okay? Let's say x, just for the sake of giving a simple example, let's say a function of x1 and x2 is x1 plus 2x2. What would happen if I were to apply the permuting operator on that function? What would I get? Anytime I see an x1, I'm going to replace it by x2, right? Anytime I see an x2, I replace it by x1. So x2 plus 2x1. Is that related to, is that equal to plus f or negative f? It's not, right? So this function f, we say, is asymmetric. Okay? That's what we mean by asymmetric. What about function g here? If I were to switch labels, instead of x1, what do I get now? x2 minus x1. And instead of x2, I have x1. But what is x2 minus x1? Okay, so that's just the negative of x1 minus x2. So that's just negative g. So we say that g is an antisymmetric function as far as the exchange of labels for electron 1 and 2 is concerned. How about this function h here? P12 operating on function h. So here I see an x1. What do I do with that x1? Replace that by x2. Here I see an x2. What do I do with that? Replace it with x1. And that's just the same thing as x1 plus x2. And that's just h. So we say h is symmetric. And g is antisymmetric. Okay? So mathematically, any wave function that describes indistinguishable particles, okay, must be either symmetric or antisymmetric with respect to the exchange of those particles.